Hey there, Calc 2 folks, back here with what is the last lecture this semester, last video lecture here, where we're going to wrap up our Chapter 13 study, looking a little bit at some, what we would say is some additional surfaces that we can encounter in three-dimensional space, surfaces beyond the case of the planes or the case of planar surfaces, right? What we're going to focus on in this section are the surfaces that we're going to encounter known as cylinders and what are known as quadratic surfaces, folks. So, again, what we are preparing for is we are preparing for coming back to the Calc 3 material, where the first two sections we encounter are going to be looking at vector valued functions, which is describing curved paths in three-dimensional space, and then a study of multivariable functions in the following chapter. This is chapter 14 and chapter 15 respectively, where we're going to be looking at, with multivariable functions, describing those in three dimensions as surfaces. And we're going to encounter some very common surfaces in a lot of our work. There are some common surfaces that arise in our work, right? And those surfaces are often the cases for what we call cylinders and the cases for quadratic surfaces, although we will encounter other situations also. All right? We want to be familiar with these type. Now, in terms of what it means to be a cylinder, this is our definition for a cylinder. Right? A cylinder is going to be just a surface in R3 that forms parallel to one of the coordinate axes of R3. Right? It's going to run right along with one of the coordinate axes. Right? It's going to run parallel to that axis. And in R3, they are expressed as what we would see as a two-variable equation. Right? With the missing variable of R3 describing the axis of parallel behavior, and the given two-variable equation describing what we think of are the cross-sections orthogonal to this parallel axis in two-dimensional space. Right? When we see a two-variable equation, we want to recognize that two-variable equation when discussing surfaces as a surface known as a cylinder. It's this unique case of a surface that runs parallel to one of the axes in three-dimensional space. And how you can tell what axes you run parallel to is that will be the variable that is missing from your equation. And when you think about what this the surface would look like, it's essentially going to be the cross-section orthogonal to this parallel axis that is being extruded, we think of as being extruded along that parallel axis. All right? Let's look at a couple of examples here, right, to help explain what we're going to see in the case of a cylinder. And here's our first example illustrating a cylinder, right, in three-dimensional space. If we consider this to be a surface in three-dimensional space, if we consider this equation here to represent a surface, what we will note is that this equation only involves two variables. If we're looking at a surface in three-dimensional space, we are looking at a behavioral description that should involve three variables, where in the case of a cylinder, one of those variables is being allowed to be it's allowed to be any value it wants to be and have no effect on the relationship, right? Its value is completely excluded from the relationship seen in the equation. Here, we see that we have a two-variable equation that is missing the variable of x. X is, in a sense, allowed to be whatever value it wants to be here. And it's not going to have any impact on this relationship that we see that only appears to exist between the values of y and z. Right? If we think about this as a surface in three-dimensional space, this will be a surface known as a cylinder that is going to run along parallel to the x-axis in our system. All right? Where if we think about its cross sections orthogonal to that x-axis, all of the cross sections orthogonal to the x-axis will look like this equation here, what its graph would resemble if we were just to consider sketching the graph of this in the YZ coordinate space. Now you might recognize that in the YZ coordinate space as the graph of a parabola. All right? In fact, if we solve it for z, we will see a very specific parabolic description come about. Right? What we do notice in this case is for a cylinder in R3 forming parallel to the x-axis in R3 with cross sections in the YZ plane forming orthogonal to the x-axis in the shape of the following parabola here. Right? This parabola does fit that format that we discussed in the case for conic sections. What we are going to see in a lot of these cross sections are the situations involving conic sections. So this is going to be this conic section z equals negative 1/4 y squared in the xy plane, which is a parabola that forms around the z-axis, right, with a focus at the location 0, -1. And remember, we're obtaining that from our information about p in this denominator. And remember, this is fraction is in the form 1/4p. And here we can see p is going to be -1 in value. The negative out in front highlights that our value of p would actually be -1. And the directrix described by the line z equal to 1. All right? This is the description of the parabola that is going to, in a sense, extrude itself along the x-axis, right? Running or forming what we say is parallel to that x-axis. If we look at its illustration, right? Here's the illustration of that surface, right? What we do see here is that we are this parabolic shape, right? We are the shape of this cross section seen in the YZ plane with a focus at at 0, -1 with respect to z, and a directrix given by the equation z equals +1, right? We are this parabolic shape in this space, the YZ plane described by this focus and this directrix, where that parabolic shape is being extruded, right, parallel to this x-axis. It's forming parallel to this x-axis in three-dimensional space. The only dependent values in the relationship happen to be the values of y and z, and y and z are always going to depend upon themselves, regardless of the location here along our x-axis in this parabolic shape. Right? The parabolic shape described by this parabolic equation. Right? This is the idea behind a cylinder. This surface is forming in space here, running parallel to this x-axis. Right? It's a surface that only depends upon the values of y and the values of z. Right? X can be any value, and you're going to see the exact same cross section at that value of x. That's going to be this cross section seen here. All right? If we look at another example of a cylinder, right, we might consider the surface in R3 described by this equation: 2x squared plus 8z squared equal to 32. In this case, you'll notice you have a two-variable equation that is being used to describe a surface in three-dimensional space, where that two-variable equation involves the values of the variables x and z from three-dimensional space, but is missing the variable y in its description here. All right? Which means this is a cylinder shape that is running parallel to the y-axis in space. And if we think about the cross sections that would form orthogonal at a right angle to that parallel axis, they would all be described by this relationship here seen between x and z, where if you spend a moment with that relationship, you would take note that that describes an elliptical behavior between x and z. All right? Dividing both sides by 32, we will get the equation for an ellipse, right? This is the case for a cylinder in three-dimensional space forming parallel to the y-axis, where the cross sections are going to exist here in the xz plane because our equation involves variables x and z, right? Which are going to be forming orthogonal to the y-axis in the shape of an ellipse, where if I divide both sides by this 32 to make 1, the result on the right-hand side, I will build this equation that resembles the equation for the ellipse in the xz plane. And because the value under x is larger, that is going to be our major axes, right? And we're going to see our major vertices along that axis at plus or minus 4, 0, the square root of 16. And our foci are going to be located, well, and our minor axes are going to be with respect to the z-axis, right, at plus or minus 2. We're going to describe these as xz coordinates here. So that would be at 0, plus or minus 2 would be our minor axes, 2 being the square root of 4. As for our foci, then, they will occur along the major axes, which will be the x-axes. And what you're going to do is take the square root of the difference of these two denominators, 16 minus 4, the larger minus the smaller, right? So it's going to be the square root of 16 minus 4, well, that's the square root of 12, which simplifies to 2 root 3. So our foci are going to be located at plus or minus 2 root 3, 0, with respect to being an xz coordinate. If we sketch this ellipse in the xz plane, orientating z vertically, right, keeping x with that horizontal interpretation, this would be the illustration of the cylinder and its corresponding cross sections perpendicular, or what we say is orthogonal to the y-plane, or sorry, the y-axis, right? Running right down the center of this elliptical shape, right? Running out of the screen towards us and running into the screen away from us is going to be the y-axis. And this elliptical shape is just going to extrude itself out along that y-axis. If you notice here, this shape is running parallel to this y-axis in its three-dimensional description. And what we're highlighting here in the illustration is that cross-section that is happening orthogonal to that y-axis. At any location we want to place it at along that y-axis, the cross-section orthogonal to that y-axis will always be this elliptical shape here. Where what did we say? We have an elliptical shape with major vertices on the x-axis at plus or minus 4, 0. Minor vertices at 0, plus or minus 2. And foci at plus or minus 2 root 3, 0, which is right about here and right about there on our x-axis. You can see those two locations just barely showing up in the graph as focus, right, or as the foci of this graph. All right, all that coming from this, two-variable description of the surface, right? That two-variable description describes the shape of the cross-sections, and the missing variable tells us what axis those cross-sections run parallel to form our surface. Here forming what we would say is this elliptical cylinder in shape. All right? Now, if we consider the case of a quadratic surface, it's defined as follows. And up to this point, this might be the most complex equational form you could obtain, right? Involving three variables x, y, and z, where you can see that you do very much see here a bit of a quadratic behavior in your variable values. All right? A quadratic surface in three-dimensional space is a surface described by this general quadratic formula, right? Or really, I should maybe say here form, so we don't get it confused with the quadratic formula from our studies of algebra, right? By the general quadratic form in three variables for variables x, y, and z given by this form here, where you have ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus j all equal to 0. where those capital values of those capital letter values, those are just constant values, right? They are the constant coefficients for the terms x squared down through z, and they are just the constant value for the value j itself. And what does have to be true is that a through f, right, those coefficients a, b, c, d, e, and f are not allowed to all be zero simultaneously. If these all turn to zero at the exact same time, this entire first portion of this form will be zero, and what you'll be left with is just this last bit. Where if you spend a moment looking at that last bit, that is the description of a plane in space and no longer going to be the description of a quadratic surface. A quadratic surface comes from adding onto a plane a bit of a quadratic behavior. And what is quadratic behavior is when occurring when you take any one of your variables and you multiply it by some other variable or itself, like y times z or x times z or x times y, are illustrating that quadratic behavior in your variables, as well as z squared, y squared, and x squared in value. All right. This is how we define quadratic surfaces. Now, we're not going to delve into the intricacies of each little bit of this. What we are going to do is kind of consider the common situations. And there are some common surfaces that we encounter in our study. Right? What we do note is there are some common occurrences of these surfaces. All right, and those common occurrences of these surfaces have cross sections parallel to one of the coordinate axes. Well, have cross sections parallel to the coordinate axes, resembling the shapes of what we know as conic sections. Right? Where these conic sections are going to be used to name these quadratic surfaces. Right? And to understand the shape of these common quadratic surfaces, we're going to explore the different shapes of the cross sections we get of these surfaces with the simple planes in R3. Right? Now, what is a simple plane? As we said, this equation, back end of this equation here, is what describes a plane. A simple plane is one where g, h, or I are the only variable values that are not zero. G and h are either zero, or I and h might be zero, where just one variable will be left inside your equation. That will be a case for a simple plane, like x equals 4 is a simple plane, or y equals 7 is a simple plane, or z equal to -8 is a simple plane. All right? The most common simple planes are our coordinate axes that occur at x equal or y equal or z equal to 0. And those are the ones that we usually maybe start our exploration with when looking at these quadratic surfaces. But you do want to also branch out and start to try to understand the surface as a whole, where you can make sure that you are locating yourself appropriately with a particular cross section. All right, so we might consider this surface given here in three-dimensional space. What we do note is this does fit this form above. We have the ax squared plus the by squared plus the cz squared part. That's these first three terms. -1 at the constant term, well, that's this plus j part, all equal to 0. The parts seen here, dxy through iz, these terms here in the middle are all have values of 0 for these constant coefficients. All right, which produces this quadratic surface. And if we think about what that quadratic surface would resemble, we would start to think about what would be its cross sections with some of the simple planes. All right, now this is a quadratic surface, right, with the equation matching the general form in the definition given above. Now this quadratic surface has cross sections with simple planes in the third dimension described by the shapes of circles and ellipses. All right, how do I know they resemble circles and ellipses? Right, is I can intersect these surfaces with some simple planes like the plane z equal to 0. Now, to intersect the plane z equal to 0 with this surface here, to understand that algebraically, all I have to do is take the value of 0 for z and substitute it into that equation for 0, or for z. So if I put 0 into this equation seen here for the surface at z, if I make z 0, this whole term will disappear and I'll be left with x squared plus y squared minus 1 equals 0. And with adding 1 to both sides, I can actually prepare this equation here, which you should be quite familiar with as a Calculus 2 student, right? X squared plus y squared equal to 1 is the description of the unit circle in the xy plane, right? If we intersect this quadratic surface with the simple plane z equal to 0, we do get a circular shape. We get a circular shape that resembles the unit circle. And in fact, we could start to notice if we intersect any plane with respect to z equaling some real number value with this surface, right? If we intersect any simple plane along the z-axis with this surface, we'll always obtain a circular shape at the center. This will always turn into some constant, right, that we will be able to subtract from both sides, right, where x squared plus y squared equal to that constant describes a circle centered at the origin with a radius of radius squared equal to the right-hand side. Right, here we had the case for the unit circle, right? If we intersect this equation with the other cross sections or some other simple planes like y equals 0 or x equals 0, right? If I make x equal to 0 or y equal to 0, I'm going to see some very similar looking equations, right? In terms of either x and z for the first equation or y and z with respect to the second, where the only difference is using x or y in the equation, right? X squared or y squared as this first term. And what do these equations describe? We might recognize these as the equations for an ellipse, right? This ellipse being in the xz plane, this ellipse being here in the yz plane, right? Both ellipses here have a major axis either on the x-axis or the y-axis with a vertice at plus or minus 1, 0, or well, both plus or minus 1, 0, and then a minor vertice along the z-axis in both cases at the square root of 1/4, which is 1/2, plus or minus 1/2 along the z-axis. Right? That's going to describe these ellipses, right, in those planes respectively. So if we think about these planes coming together in their description of the surface, this is what we call elliptical surface. And in fact, you can notice this would happen for any of these simple planes. Any simple plane along the y-axis will look like an ellipse, or any simple plane along the x-axis will look like an ellipse now there are certainly some limitations on this. As you would note, these are going to be positives, and when subtracted, they're going to turn into negatives on the right, where you can't necessarily have circles with negative radii or circle or ellipses with negative radial properties, right? But if we look at these overall in terms of their description of shape and combining those descriptions of the conic sections, we can start to visualize our surface seen here, where we see those two elliptical shapes happening with respect to x and z and y and z respectively, right? Here's y, here's z, so here's y and z's ellipse. Here's x, here's z, so here's x and z's ellipse, right? All coming together right in the center of this shape, where along this outer border, right, we have that circular conic section. And we would notice along any height of z, you would always encounter a circular cross section where z is some value between -1/2 and 1/2, and between any x or y value, you would, between -1 and +1 for x or y, you would always have a respective elliptical shape dependent upon that x or y value. If we think about what these conic sections look like above in their descriptions, right? This would be the 3 conic sections that we are illustrating here with these cross sections of our surface. And if we think about arranging these coordinate planes to describe a 3-dimensional space, notice this is the xz plane, this is the xy plane, and this is the yz plane. If we were to arrange those appropriately to describe our 3-dimensional space, they would start to describe the boundaries on this elliptical shape. All right. If we were to look at one more example here, right? Here's another quadratic surface, right? Where we notice again that looks a little like what we have above. Right? We have our first 3 terms, and then we have our constant term. And most of the common ones do ignore these middle terms, but occasionally you will see these appear in your work, and what these cause are some shifting and skewing of your shapes, right? Which are a little less common, right? But you would notice this would cause some of your shifting, and these would be results of skewing your shape, right? Taking an ellipsoid and kind of skewing it in one direction or another, kind of making it slanted in one direction or another, or shifting it about in space would be caused by these changes, right? Where when we ignore those middle terms, we do get a bit more of a common shape. We're going to see these cross sections look a little bit more like a conic section specifically, right? Here we can see that this is going to take on the shape of, if we start to look at our simple planes, if I look at all my simple planes for x, and what would we have here for y and squared and z squared? Well, that would be a hyperbolic shape with respect to y and z. If I was to make y a simple plane, well, this would turn into a constant. And I'd have an equation involving x and z here that would look a bit more elliptical. And then if I was to come along and look at the simple planes for z, this would, between x and y, would take on more of a hyperbolic equation again. And what we have here is what we might say is a set of conic sections that looks like ellipses and hyperbolas. And what this surface might be called is an elliptical hyperboloid. Right? If we put this together, right, with some of the simplest of our simple planes, that being where our variables could equal 0, right? When z equals 0, we have this this hyperbolic description, right? We have this hyperbola that forms in the xy plane, right? With major vertices, well, just vertices at plus or minus 6, 0 on the x-axis, and foci also on that x-axis, taken from the square root of the sum of these denominators, the square root of 40 plus or minus, which does simplify to 2 root 10, right? If we were to look at, oh, and I forgot to mention the asymptotic behavior here. We might also say here, and asymptotic behavior described by what would be y equals sorry about that, folks. Yeah, so we want to make sure we get these asymptotic descriptions in here, where in this case y is going to change by 2 and x is going to change by 6, which does simplify to 1/3 in value in its description. All right. So yeah, we do also have an asymptotic behavior that we want to take note of when noting on hyperbolas. All right. So that would be the description of the hyperbola in the xy plane. The hyperbola seen in the yz plane would be described as this. Now I have to get my variable in there. It's a common mistake. We're here our asymptotic behavior is described by z equal to plus or minus 1/2 y. Looking at the denominator here, note this denominator is 1 in that hyperbola. So that does lead to this vertex here at 0, comma, plus or minus 1, right? And a foci given by the, what? Square root of the sum of these two values again. That's plus or minus 5, root 5, all occurring on the at a yz coordinate along the z-axis at plus or minus 1 and plus or minus the square root of 5. And then that asymptotic behavior happening with respect to the z-axis being vertical, right, and y being horizontal in this description with a slope of plus or minus 1/2 y. All right. If we then consider the cross-section in the simple plane where y equals 0, there we said we'd get more of an elliptical equation, and that is what we see here, right? Again, if we put that 1 into that denominator, we have this description of an ellipse. All right? Major foci along the x-axis at plus or minus 6, comma 0, major vertices at plus or minus 6, 0, minor vertices at 0, comma, plus or minus 1, and notice the overlap in these locations, right? There is some common overlaps happening in these locations of the vertices in these different illustrations. All right, where in this case in the ellipse we're going to have a foci at the square root of the difference of 36 and 1. That would be the square root of 35. And asymptotic. Now here, what did I do? That's what I mixed up. I brought the asymptotic behavior into the wrong location. So that doesn't have asymptotic behavior, right? We should just note and foci given by x comma z equal to plus or minus the root 35 comma 0. Now, since the cross sections are ellipses and hyperbolas, with really the hyperbola being the dominant cross section in its description, right? This becomes known as a hyperboloid. That's from the two hyperbola cross sections. What we'll do is go a little bit more descriptive by describing that third cross section in there by saying it's an elliptical hyperboloid. All right? This cross section, or this shape seen up above here, had two dominant elliptical cross sections. So it was an ellipsoid, and since the third cross section was circular in shape, we could say here this was a circular ellipsoid. Right? Now let's go down and look at this elliptical hyperboloid. Right? What does an elliptical hyperboloid look like? Here's the shape of an elliptical hyperboloid. Right? It's this, right, shape in space where certainly in the two cross sections with respect to z and x and with respect to y and z, we have these hyperbolic cross sections, right, seen below here with these two cross sections. Right? And in that third dimension, with respect to just x and y, we have this elliptical cross section. And that would remain true across this whole shape. If we were to take our simple planes along the y-axis, they would all look elliptical. And if we were to take our simple planes along the either x-axis or the z-axis, right, up the surface, they would look like these hyperbolas, right? Well, they would look like a hyperbola, similar in shape to what we see here. All right? Again, folks, putting our understanding of these cross sections together in these locations in space with, right, the understanding of these forming in 3 dimensions is going to help us understand what this 3-dimensional shape looks like. As I said, if we arrange these 3 separate cross sections, because notice these are our coordinate planes. If we were to put these coordinate planes in the 3-dimensional space arranged appropriately, right, we would see the descriptions of these cross sections starting to describe the behavior of this surface. And the more cross sections we would have, the more of this surface we would have in its description. All right. So again, folks, what we're looking at here is our last idea, which is just starting to introduce us to these surfaces, these other surfaces that are something other than planes in space. And these are what we call quadratic surfaces. Now, there are more other common shapes. We only looked at two examples there of quadratic surfaces. There's also the paraboloid. That's where your two common cross sections might be parabolas, and then the third cross section might be an ellipse or circular in shape. So you might have a circular paraboloid or an elliptical paraboloid, right? And then you have spheres, right? That's where, all your dimensions, all your cross sections are circular in shape, folks, right? And we get these different descriptions of what we would call our quadratic surfaces, right? The common simple cases. Ones without shifting, right? And ones without skewing. When you start to skew, you do have to account for the skew in the shape. And when you do start shifting, you have to start to look at other locations in the space to identify where your surface might exist. All right. And then don't forget our cylinders, folks. You're also going to see cylinders as you move on into Calc 3. Right. These cylindrical shapes or surfaces will also be part of our study. And we have to know how to recognize those, and those are going to appear in three-dimensional space as two variable equations. Again, where the cross-section, right, is going to help us to understand the shape of that surface in 3 dimensions. And the missing variable is going to be the axes that surface runs parallel to in that space. And will be this cross-section will be perpendicular to. All right. So, folks, that is it. That wraps up the semester. You'll notice this is where we are making use of that work with conic sections quite heavily. And then this is all going to come back to us. This last few sections of material in Chapter 13 are going to be there when we return in Calc 3. We're going to start in with talking about vector-valued functions. That is our lines in space, our lines and curves in space, right? N-dimensional space if we want to take it that far. And then we're going to be looking at surfaces in 3-dimensional space. And what are some of the simple surfaces we're going to encounter? Well, it's going to be planes, and it's going to be these quadratic surfaces or cylinders. Right? We certainly will see more complex surfaces than these presented, but we want to be able to recognize these simple scenarios. All right? These will come back when we start to study multivariable functions. All right? This is a multivariable relationship that could be thought of as being a multivariable function, and really more specifically these would be, this illustrates a multivariable relationship where there's potential for it to be functional, right? Depending upon the limitations we put on our domain in this scenario. All right? So, folks, I will end there. In fact, I got to jump into a lecture, or well, not a lecture, but some office hour times, and to start to wrap up my semester. But that is it, folks. I hope you're all doing well. Hope you're hanging in there. If you have any questions, you know where to find me and collaborate over the next couple of days. And I'll be working on grades and getting all that up to date, and be waiting for your next test to be coming in. So that, and you also probably have some surveys out there. If you've encountered any of the surveys, please make sure you're taking those surveys, folks. All that information is extremely helpful. I may be even asking you a survey through Blackboard. Please fill out those surveys. I can use that information, all right? And then again, I am also up for promotion next year, and I'm going to be using some of that information in promotion to petition for my promotion. So, again, I hope you're all doing well, and I'll see you all next time.